Welcome to Fourier series expansions with eigenfunctions. So the quick definition, the Fourier series for function f on the interval negative L to L is given by f of x. I'm going to actually use a capital F here. Capital F of x is equal to a naught plus the sum from n equals 1 to infinity of a sub n times cosine of n pi over Lx plus b sub n times sine of n pi over Lx, where a n and b n have rather specific formulas. So where a naught is equal to 1 over 2L times the integral from negative L to L of f of x dx. The remaining a sub n are equal to 1 over L times the definite integral from negative L to L of f of x times cosine of n pi over Lx dx, and our b sub n's are 1 over L times the definite integral from negative L to L of f of x times sine of n pi over Lx dx. So just a quick note, these a sub 0, a n, and b n are precisely what we would need for this series to basically be the original f of x. So note, these coefficients are precisely the coefficients we need for our Fourier series. I apologize, I need to update my video. And again, so again, these are the coefficients that are needed for our Fourier series capital F of x to essentially equal lowercase f of x, the original function. So we can kind of show that briefly. So if we assume lowercase f of x is equal to a naught plus the sum from n equals 1 to infinity of a n times cosine of n pi over Lx plus bn times sine of n pi over Lx. Then if we go ahead and apply a variety of different integrals, so if we just do the integral first. So if we apply just the integral from negative L to L dx to both sides, then we get that the integral from negative L to L of f of x dx is equal to the integral from negative L to L of a naught plus the sum from n equals 1 to infinity of a sub n cosine of n pi over Lx plus b sub n sine of n pi over Lx dx. We're going to apply a little sort of theory here that we haven't seen. We're essentially going to toss that integral inside of our summation. This is the integral from negative L to L of a naught dx plus the sum from n equals 1 to infinity of a sub n times the integral from negative L to L cosine of n pi over Lx dx plus b sub n times the integral from negative L to L sine of n pi over Lx dx. Note the integral from negative L to L of cosine n pi over Lx and the integral of negative L to L of sine of n pi over Lx are both 0, as we saw in the orthogonal functions video. So these integrals are both 0. These are both equal to 0 since 1 cosine n pi over Lx and sine of n pi over Lx are orthogonal functions. So there's a reason that we did all of that work in the previous video. We are using this orthogonality to show that these coefficients make sense. So what we get then is that the definite integral from negative L to L of f of x dx is equal to just a naught times the definite integral from negative L to L dx. This is just 2L times a naught on the right-hand side. And so dividing through by 2L, we get that a naught should just be 1 over 2L times the definite integral from negative L to L of f of x dx. Similarly, if we instead apply a definite integral from negative L to L of something times cosine of n pi over Lx dx. Then this will become, we get the definite integral from negative L to L of f of x times cosine of n pi over Lx dx is equal to the definite integral from negative L to L of a naught times cosine n pi over Lx. Actually, I'm going to call these m pi instead of n pi. One moment. Let's change our constant to m instead of n. So we have a naught cosine m pi over Lx plus the sum from n equals 1 to infinity of a sub n cosine n pi over Lx times cosine m pi over Lx plus the sum from n equals 1 to infinity b sub n times sine of n pi over Lx times cosine of m pi over Lx, all inside that definite interval, so any with dx. Again, 1 cosine n pi over Lx and sine m pi over Lx are all orthogonal. So, but 1 cosine of n pi over Lx and sine of n pi over Lx, or sine of m pi over Lx, this whole set, these are all orthogonal. So what we get is the only piece that does not go to 0 is the place where n and m are equal. So the only non-zero part of the right-hand side is the cosine term with n equals m. So it is the cosine term with n equals m. For orthogonal functions, doing the integral with a function times definite integral from negative L to L with a function times itself doesn't have to give 0. It's only when we use distinct functions. So what we then get is that the definite integral from negative L to L of f of x times cosine of m pi over Lx dx is equal to the definite integral from negative L to L of cosine, of a sub m times cosine squared of m pi over Lx dx. But we can go ahead and use our trig identities and take this integral. Using our double angle formula, this becomes the definite integral from negative L to L of a sub n times 1/2 times 1 plus cosine of 2m pi over Lx dx. Again, this was using our double angle formula. So we are looking at a sub m over 2 times the definite integral from negative L to L of 1 plus cosine of 2m pi over Lx dx, or am over 2 times x plus L over 2m pi oops, sorry about that, times sine of 2m pi over Lx, evaluated from negative L to L, or between negative L and L. Again, we are looking at am over 2 times, we would have L plus 0 by plugging in our L. sine of 2m pi will be 0. It's an integer multiple of pi inside. And then we will subtract off negative L plus 0. This winds up simplifying to just am over 2 times 2L, otherwise known as am times L. Solving for am, we wind up getting, therefore, that am is equal to 1 over L times the definite integral from negative L to L, f of x cosine of m pi over Lx dx. We can use a very similar logic for sine. So similarly, if we instead apply definite integral from negative L to L of our function times sine of m pi over Lx dx, we wind up with definite integral from negative L to L of f of x times sine of m pi over Lx dx is equal to the definite integral from negative L to L of a naught times sine of m pi over L x dx plus the sum from n equals 1 to infinity of an times cosine n pi over Lx times sine of m pi over Lx. Then we have plus the sum from n equals 1 to infinity of b sub n times sine of n pi over Lx times sine of m pi over Lx. That whole thing then followed by dx. Once again, on the right-hand side, the only term that will be remaining is the sine m pi over Lx times sine m pi over Lx. So again, due to the orthogonality of the functions, so the orthogonality of 1 cosine n pi over Lx and the sine functions m pi over Lx. Due to this orthogonality, the only non-zero term on the right is the sine term with n equals m. So once again, we wind up with a definite integral from negative L to L, f of x times sine of m pi over Lx dx is equal to the definite integral from negative L to L of b sub n times sine of m pi over Lx times sine of m pi over Lx, otherwise sine squared of m pi over Lx dx. Again, applying the double angle formula, this is just the definite integral from negative L to L of b sub n times 1/2 times 1 minus cosine of 2m pi over Lx dx. I apologize, I need to update my screen. Taking this integral, we are looking at, Switching back. So again, we use the double angle formula for cosine double angle formula. Here, applying the integral, we're looking at bm over 2 times, we would have 1 would go to x. Negative cosine 2m pi over lx would go to a negative L over 2m pi sine of 2m pi over Lx. And then we evaluated negative L and L. So this would be Bm over 2 times L minus sine of 2m pi is just an integer multiple of pi. So we're subtracting off 0. And then we will subtract off negative L again minus 0. I apologize, this is not updating correctly. Going just slightly further, we wind up with, so we had Bm over 2 times L minus 0 minus negative L minus 0. So this becomes B sub m over 2 times 2L, or in other words, B sub m times L. So if we then divide through, our left-hand side was negative integral from negative L to L of f of x sine m pi L over Lx dx. Dividing through by L, we wind up getting that our B sub m should be equal to 1 over L times the definite integral from negative L to L of f of x times sine of m pi over Lx dx. So this is just a useful trick to have. Again, everything I had after the initial definition, this was all just showing sort of why these coefficients are what they are. Ultimately, we just need the series and the coefficients, and we can just evaluate these each time. So you do not have to rederive these formulas. These are your formulas for the coefficients for the Fourier series for f on negative L to L. Just a quick comment. I did say that these coefficients are what we need for capital F of x to essentially equal our original function. In a future video, we will talk about where the slight differences occur. In the next video, we will do an example where we go through and actually calculate what our Fourier series should be.